We know that buffers work by keeping the pH of a solution relatively constant, or by having minimum changes in pH when an acid or a base is added to the buffer solution. Now, how effective a buffer is going to depend on the buffer range and the buffer capacity. The buffer range is just a pH range, like a range of pH values where the buffer is still neutralizing added acid or added base by still maintaining that pH relatively constant. Now the buffer capacity is like how many moles of added acid or added base that buffer can actually neutralize without having significant changes in the pH value of the buffer solution. The how effective a buffer is going to depend on the ratio of your acid, the weak acid that you have in the buffer solution, and the conjugate base of that weak acid. Ideally, the best range that you can have is when the concentration of the acid, the weak acid, and the conjugate base, it's equal. Those two concentrations equal to each other means that that buffer solution will be able to neutralize the same amount of added acid and added base. Any buffer that it's able to neutralize added acid or added base in a range of pH going from 1 unit less than the value of your pKa or 1 unit of your pH value above that pKa value that you have, it's still an effective buffer. So with the example that you have at the end of the page, you can see what I mean with that range, like 1 unit less or 1 unit above. So if you have benzoic acid, which is one of the acids that we used previously in an example, you have the Ka value for that weak acid, 6.5 times 10 to the minus 5. If you're not given the pKa, you can calculate the pKa from the Ka value. The pKa will be minus log of your Ka value. So you have the pKa right there, it's 4.187. If you prepare a buffer solution containing benzoic acid, you're given the pKa value, you have that number. That buffer will work effectively from keeping your pH value from 3.187 all the way to 5.187. In that range, your buffer will be working effectively. So to find out, like you can plug in numbers in your equation. This is the Henderson-Hasselbalch equation. So you can plug in a pH value of 5, you have your pK value, and then you can solve for that ratio of conjugate base and acid that you need to have a pH value of 5, for example. And you can set up like how much or what concentration of your weak acid you need, what concentration of the conjugate base you need to add to that solution to have your buffer solution at a pH of 5, adding acid or adding base to your buffer solution, and that buffer solution still keeps the pH at a value that is still close to the initial 5 pH value. So if the value of the pKa for an acid is 3, your buffer will still be effective if you have a pH from 2 all the way to 4. The second thing, not just the ratio that you have for the concentration of the weak acid and the conjugate base, not just that, Another thing that will make an effective buffer is the amounts that you have for the weak acid and the conjugate base. So for example, the higher the concentrations of your weak acid and your conjugate base, the higher the amount of added acid and added base that you can have with your buffer solution, neutralizing those added amounts and still keeping the pH relatively constant. So you have two diagrams here. The one on the left, and I'm representing my weak acid with two dots. The red and the blue represents the conjugate base, which is just the negative part of your acid. So you get to see in the diagram that you have a mixture of your weak acid and the conjugate base for both of them. Now the one on the left, you have a higher concentration of the weak acid and the conjugate base, which means that for the solution that I have represented on the left side of the diagram, that one can neutralize a larger amount of added acid or added base. The added acid will react with the conjugate base. Any added base will react with the acid that you have in solution. Something that we look at is titrations, because you will see like with the graphs that when you have a titration, whatever you're adding, it can be an acid, or you can be adding an acid to a base or base to an acid. You will have a region or a part in your titration where you have a buffer solution. The pH will remain relatively constant until some point where the buffer is not acting as a buffer, or your solution is not acting as a buffer anymore, and you get to see significant change in the pH value. So here I have just some definitions for titration. Most of them you already know. What is the titration? What is the titrant, which is the solution that you're using to do the titration? The analyte, the solution that you have that you're titrating with, the titrant. Equivalence point, this is something that we're going over in the calculations. Equivalence point is that point in your titration where the concentration of the acid is equal to the concentration of the base. And the end point is where we get to see an actual color change if we're using an indicator, which is not the case for all titrations. Some of them we use an indicator. In some of them we just use a pH meter to determine pH value and how that pH value is changing as we add any like titrant to the solution. So I'm going to show you examples for pH curves, okay, which is just a graph. So a pH graph is just a graph that is showing you, okay, you have a solution at an initial pH, and now you're adding the titrant to your solution or the analyte. The pH is going to keep changing as you're adding the titrant. So if you have your analyte, it's an acid, and you're adding a base to your acid solution, acidic solution. Your initial pH corresponds to the pH of an acidic solution. So you have a pH that it's like in the range of 0 to 3. Now you start adding a base and that pH starts increasing because you're adding a base. So the pH, that graph, your pH curve, is just showing you how the pH changes as the titrant is added to your initial solution. Here you have a representation of your pH curves. I have two different ones and we have an additional one in the next slide. The first one that you're looking at here, it's a graph that corresponds to a strong acid titrated with a strong base. In your graph, what you have in the y-axis is the pH value, and then the x-axis is the volume of the base that you're adding. So for both of them, the titrant is a base and you're titrating an acid. So you need to be able to identify which graph represents what type of titration. So there are several things that you can be looking at. First, you can be looking at your initial pH value. For both of them, we have a strong acid, which means that the initial pH value is a pH value corresponding to a strong acid. That initial pH value, it's a pH before adding any base, which means that if you have a strong acid, that pH value should be a low number. So I have here my initial pH value. I have here initial pH value in the beginning of your graph. That's one thing that you need to be looking at. If it's a weak acid, that pH value will be closer to 2 or 3. So between 2 and 3, 3.5. That's the initial pH value for a weak acid. Now, you start the titration adding in the first graph here a strong base. The pH starts increasing. In the beginning in your graph, you can see that that pH value is not changing by a significant amount. Okay? And then you can see in your graph that there's a jump. That jump right there represents the equivalence point of your titration. In the middle part of that jump in your graph, you can identify the equivalence point or the pH at the equivalence point for that specific titration. That's another thing that you need to be able to identify in your titration plot. For a strong acid titrated with a strong base, that equivalence point happens always at a pH equals to 7. So your equivalence point at a pH equal to 7 represents a graph for a strong acid titrated with a strong base. Now, when you look at the second graph, if you check your equivalence point where the jump is happening, right in the middle of that jump, if you move to your y-axis, your pH is going to be closer to 6 than to 7. It's an approximation. pH lower than 7 at an equivalence point at a pH lower than 7 always represents a titration of a strong acid with a weak base. You see how your pH is lower than 7. 7 is your neutral pH. That pH value is going to be determined by the strong one. In the first graph that you have, the equivalence point is happening at a pH equal to 7 because you have a strong acid and a strong base. They're neutralizing each other to get a neutral solution with a pH equals to 7 at the equivalence point. In the second one, you have a strong acid titrated with a weak base. Remember, your strong acid dissociates entirely, which means that your pH is going to be lower than 7 or acidic at your equivalence point. So the first thing that you need to be able to check in your graphs, it's an initial pH for your acidic solution. The second thing is the pH at the equivalence point in your titration. Now another thing that you can check is that final pH. You see how in your graphs that part remains relatively constant there. So you can estimate, you can move somewhere here below 12. This one is happening close to 12, a little bit higher. Higher or close to 12. Strong base. So remember, the higher the pH, the more basic or alkaline something or a solution is. In the second one, a weak base, and your pH is below 12. So initial pH at the equivalence point, and your final pH in your pH curve. Those are the three things that you can use to identify which type of titration is that graph representing. So the third one that I have here is one that we're going to use to show you actual calculations with this pH plots. So you have a representation of a titration curve of a weak acid titrated with a strong base. So you have strong with strong, you have strong acid with weak base, and now this one, weak acid with strong base. You can see that your initial pH here, look, it's above 2. Now your pH at the equivalence point, I have right in the middle here a value, estimated value close to 8. So here the strong one is the base, which means that the pH at the equivalence point is always determined by the strong one. So you have a strong base and basic pH are above 7. So the equivalence point for a titration between a weak acid titrated with a strong base, the pH at the equivalence point will always be higher than 7. If it's a strong acid titrated with a strong base, the pH at the equivalence point will always be 7. If it's a strong acid with a weak base, the pH at the equivalence point is always below 7. And when you have a weak acid titrated with a strong base, the pH at the equivalence point is always above 7 because the strong one is the base. Initial pH for a strong acid, it will be lower than 2. Initial pH for a weak acid, 2, close to 2, or higher than 2. Now the fourth possible combination that you can have, it's a weak acid titrated with a weak base. And I'm giving you just the 4 options of acids being titrated with something. You can also have the base being titrated with the acids, but I'm not going over those. So weak acid titrated with a weak base. Now in this case, the pH at the equivalence point, remember we're determining the pH at the, or approximating. We're not actually determining a number. I'm determining a number with the graph because I actually added numbers here. But you can always make an estimation, higher than, equal to, or below than 7. So when you have a weak acid and a weak base, for you to make an estimate of your pH at the equivalence point, you need to know the Ka values. Ka value for the weak acid, Kb value for the weak base. Based on those numbers, you can actually estimate the pH value at the equivalence point of your titration. Remember, your Ka and your Kb, they represent your equilibrium constant. That numerical value is telling you how much of your acid or your base is dissociating in solution. The larger the value of your Ka or your Kb, the larger the dissociation of your initial molecule. So whenever your Ka value is larger than your Kb value, it means that your acid is dissociating in a larger extent. So you have more hydronium than hydroxide in that solution. So whenever the Ka value is larger than your Kb, the pH at the equivalence point will be acidic or below 7. Whenever the Kb value is larger than the Ka value of your weak acid, then the pH value at the equivalence point will be above 7.